don't get too hung up on the r-squareds and the interpretations. Basically, you want to get it as close to perfect as possible. It really depends on the discipline as to what a good value is. If you're talking about psychology, where human characteristics are not highly correlated, or correlated as we would say, then seeing something under 0.5 is pretty common. Now that of course means that the relationship is not very strong. Now if you're in biology and you're relating the amount of a drug administered compared, so the drug administration, how much of it you inject compared to the effectiveness, I don't know how you'd measure that, you would want something pretty close to 100%. In other words, if you saw, points were all over the place, then sometimes adding more would make it effective. Sometimes, so there's your effective point, sometimes it would be less effective. So you really want a pretty high r-squared if you're doing things like biology or medicine. Let's go back to the example. The example asked us to answer a few questions, and we got to the point where we have our equation in there, and we have the question that we want to ask. Excuse me, let me get back to that. So there it is, Cruising USA. So we found the regression equation that models the data. We talked about the r-squared. Explain the meaning of the slope. Okay, so the meaning of the slope, well, we had r of s equals 0 or 0.3 s minus 1.3. I believe that's what we had. Let me jump back. So we need to first ask ourselves, a rate of change is the change in output over the change in input. So 0.3 over 1 is saying that as the input increases by 1, the output increases by 0.3. Well, what are the units for the input and output? The output, if you recall, is billions of dollars, and the input is a ship. So this means that a change or an increase of one ship, we estimate, or increase of one ship produces an estimated, because remember this is a regression, it's not perfect, increase of $0.3 billion of revenue. So that's what we would expect based on our analysis, and this is kind of still really an average rate of change calculated with respect to all the other data at once. So $0.3 billion per one ship. Okay, what does the vertical intercept mean? Well, remember, every vertical intercept, r of s equals 0.3 s minus 1.3. Every intercept is along the vertical axis. So if we have an input of 0 and 0 minus 1.3, we get the ordered pair 0, comma, negative 1.3. So actually, our function starts down here and has a increase going that direction. Well, this doesn't really make sense. If the input is number of ships, and this is revenue in billions of dollars, then what are we saying? If there are 0 ships, we would expect a revenue of negative $1.3 billion. So I don't know what that means exactly, and if you think about it, our data, our original data set, actually only considered ships between 134 and 167. So it's really kind of wrong of us to go anywhere outside of this 134 to 167 window. Here are kind of our data points. So anytime we go outside of that window, we can have funky predictions. And this is called, whenever you're within the input domain that you have in your data set, this is called interpolation. You're interpolating if you're talking about outputs within this input range. Anything outside of here or here is considered extrapolation. I'll put it over here too, extrapolation. Next we want to ask, sorry, I'm going to the wrong slide here. We explain the meaning of the vertical intercept. Estimate the number of ships required to generate $4 billion. Now this is going to appear to us as just 4. So we want to know, when does 4 equal 0.3s minus 1.33? We could do it two ways. We could solve it algebraically or do it graphically. I'm going to do it graphically. I'm going to plot the line y equals 4, and I'm just going to find the intersection. Looks like it's outside of my window, so I'm going to change my window a little bit because my y max only goes to 3.8. I actually want to see 4 billion. So there's that one.